All right. So I've turned the recording on. We're live. Audio and video should be, well, I think pretty much is working. We've been talking a little bit before class. So let's get started. It is a new day in structural analysis because we are done with trusses for now, and we're going to start a new topic, and probably one of the most critical topics in the class, which is shear and moment diagrams. Uh, Keeping on the same schedule with homeworks. I have here that homework 3.3 is to be graded because it wasn't graded before class when I put together the notes, but I actually think the grades are already posted. But I'll check that after class. I'll have the solution posted, and we'll keep on trucking with that schedule. And you'll have homework 4.1 assigned today, which is your first homework assignment on shear and moment. Let's get into this. Let's talk about shear and moment diagrams. This is a really important topic in the class, and it's a really important topic to structural engineers. I mean, you're getting a degree in civil engineering, and there are some things that just as civil engineers you need to be able to do. You need to be able to understand. Like, you need to understand how to run a differential level loop. That's important. You need to understand how to manipulate Bernoulli's equation and understand open channel flow, and then bearing capacity of a foundation. Like these are like seminal skills in the world of civil engineering. And in structures land, I'd argue one of the most critical skills is the ability to draw shear and moment diagram. They're very useful tools for civil engineers because they're critical to design. So I just have a random beam here on the slide, and what I have here is something you all are familiar with already, which is your what I'll call your load diagram. So here's the beam, here's the supports. We've got a 60 kip load that's concentrated, a distributed load. This is stuff that you all are familiar with at this point. And to be fair, I'm sure you've probably looked at shear and moment diagrams in maybe some other classes. Maybe you've done this in statics or deformables, but we're really going to explore it in here. I mean, we're going to be drawing shear and moment diagrams for all sorts of loading conditions and all sorts of loading scenarios. And the idea is, again, with the theme of the other stuff that we've done in here, is to try and use simple tools to analyze really complex problems. That's kind of the idea. But if for a given beam, like you see here on the slide, this is the shear diagram in the middle, and this is the moment diagram that you would get here on the bottom. And when we're done with this topic, you'd be able to draw a shear diagram like this in your sleep. It'd be really, really simple. These are critical to design. And what I mean by that is this, okay? As an engineer, it is your job, let's say you've got this beam, it's your job to size that section. In other words, what does the beam need to be? If it's a reinforced concrete beam, how deep does it need to be? How wide does it need to be? How much rebar do you put in? Do you put in 4 number 7 rebars, or 3 number 9s, or whatnot? All of that stuff is what your job as the civil engineer is. If it's a steel beam, is it going to be a W27 by 84? Is it going to be a W30 by 90? What have you? Those determinations, that's your job as a civil engineer, is to design those sections. And I would argue, you just can't design them without understanding what the shears in the moment are. For instance, if I look at this beam tells me that I have a maximum shear of 46 kips, so I need that whatever section that I size, if it can withstand a shear of 46 kips, it can hold up the shear for the entire beam. So that tells me what I need to design it for. For the moments, I know I have a maximum positive bending moment of 460 foot kips. I have a maximum negative bending moment of 100 foot kips. So I know that the beam is going to be in smiley face bending from A to this point F. And so if it was a concrete beam, I'd need the rebar on the bottom. If it was everything past F, I'd need the rebar on the top. And then, if you take concrete design, we'll talk about development length and all that other stuff. And I'm not trying to, delve into those worlds. But the idea is that these tools are critical. You can't design beams without them. It's just like trusses. Like, you can't design a member in a truss without understanding the internal forces inside it. All shear and moment diagrams are just plots of the internal shears and moments in a beam. That's all that's going on. In order to discuss this, and so let me sort of jump a little bit further in the future so that you all understand where this is going. We're ultimately going to try and develop some graphical tools to draw shear and moment diagrams. The idea is that we want to make it simple to take a structure that has what I would say relatively complex loading and knock out the shear and moment diagrams as quickly as possible. Okay, but This is one of those topics where in order to run, we need to learn how to walk first. And so the first thing that we're going to do is we're going to look at just the internal shears and moments at a particular point. Okay, so if you look here on the slide or on the screen or on my whiteboard, I have an example that we're going to do here in a second where I just have structure and I'm looking at a particular point and I'm saying, okay, what are the shears and moments at that point? Okay, and then once we determine that, then it's like, well, we got the shears and moments at a point. What about determining the shears and moments everywhere? And so that's where the diagram comes into play. Now, let's go back to something we discussed a little while ago, and it was about sign conventions. And we sort of like, I don't want to say we glossed over it, but we've talked about this before, but now we really need to talk about it. So let's talk about the image here on the top. Okay, so this image that you see right here. Okay, so this is what happens when you take a samurai sword or your lightsaber and you cut through some arbitrary point in the structure, which is what we're going to be doing. We're going to be cutting through like a random point. We're cutting through some arbitrary point and we're getting at most 3 unknowns because there's a sum of forces in the x direction, a sum of forces in the y direction, and sum of moments, so you get 3 unknowns. Now, up until now, all we've been dealing with are really the axial loads, those P forces. And so those P forces, what I'm talking about there is I'm talking about how we did, let's say, our truss analysis. So we would do a method of joints. We would look at the equilibrium at a particular joint, and then we'd say, okay, here's a member, so it's experiencing an axial load, okay? And when we did method of joints, when we started out, you know, we were doing pretty simple problems. So we had situations where we could just look at it and say, well, that member's going to be in compression, or that member's going to be in tension. Now, what happens when that wasn't the case? What happened when we had problems where it wasn't so intuitive, like members with 2 diagonals? Like you couldn't just look at it and say, well, this one's obviously tension, this one's obviously compression. Sometimes it was a little complicated. So what we would do is we would just automatically assume they were both tension. And we picked tension because that's our typical sign convention for axial loads, that we take tension to be positive. And so you can see in this image, the P values are pulling away from the section. Those are positive axial forces. So we usually treat axial forces that are tensile as positive because they tend to make the member longer, increase its length. All right. That's axial forces. What about shears and moments? Okay, well, this is our positive shear convention, or positive sign convention for shears. So when we cut a section, if we look to the left, downward forces are considered positive and upward forces are considered positive for shear. Now, to be clear, you could pick either one. Like you could have your sign convention like this, or you could have it backwards. The reason why we have it this way is because it matches the graphical techniques that we're going to explore like to a T. And so if we use this sign convention, it's going to make our graphical approaches that we deal with later a lot easier. Similar for bending moments. If we cut a section, we look to the left, we have counterclockwise moments being considered positive. And if we look to the right, we have clockwise moments considered positive. Now, this box here in yellow is kind of important. With trusses, we could sort of hop around with axial forces a little bit because it was pretty straightforward. Like we could look at the joint a lot of times and just know that that member is going to be in compression or that member is going to be in tension. With shears and moments, it's a little different. Okay, it is very important that when you're looking at your internal shears and moments that you follow this sign convention. It is critical because it will ensure that you are consistent with the graphical approaches that you use later. In other words, if you start just looking at the free body diagram and say, oh, the shear has to be upwards, it's going to cause you some mathematical problems later. I'm just telling you from experience. So I found that with shears and moments, it is vitally important to just stick with the sign convention. And if the shears are negative, then they're negative. If the moments are negative, then they're negative. And so that's going to be what we do, not just in this class, but that's just what we do as structural engineers. Okay, let's explore that by looking at this problem. Okay, so this is going to be the problem that we do in class. And then after this, I'll go ahead and tell you we do get a bit go into derivation land a little bit because I want to derive something for you because that's going to be important for what we do on Monday. But today, for what we do in class, let's look at this problem. Okay, so I want to compute the internal shears and moments for the following structure. Okay, now first off, I mean, maybe it's been a while, or maybe you don't quite remember this, but we've actually done this example before. Okay, if you go back into your notebooks and go, this is actually the very first reactions problem that we did. We did this problem when we first started doing support reactions problem. This was the first problem. So if you dig back into your notebook, you'll see that we got AY was 35.8 kips going up, and BY was 32.2 kips going up. And so we've already done part of this problem. Now what I want to do is I want to look at this from a shear and moment perspective. And so what I did is I really just, it's almost like flipping a coin. I just picked a random point on the structure. I said, let's just pick a point, I don't know, 12 feet from A, and let's determine the internal shear and moment at that particular point. Okay, and so that's what we're going to do. Now, I want to show you something here on the whiteboard, because this is really important. And it might not seem it, but I'd argue that in all my experience teaching this is kind of one of the things that trips people up the most. So here's the problem here on the board. And what like I said, in this problem, we were going to determine the internal shears and moments at a point 12 feet from this support A. Okay. And so what I did is I broke out my samurai sword or my lightsaber, and I cut through the beam 12 feet from A, and I split it up into two pieces. So this would be looking left, and this would be looking right. Okay. So the first thing that you need to do is make sure that you're comfortable with the sign conventions. And so it's almost something that you kind of have to memorize. So for instance, when you're looking at the shears, these are positive shears. So these are our unknown vertical forces inside the section. So maybe we'll call this, just call it V and V. And then our moments, these are positive. So this is positive moment, and this is positive moment. Okay, and that's something that you pretty much just need to memorize. That, always draw, when you look to the left, positive shears down, positive moments counterclockwise. When you look to the right, positive shears upwards, positive moment is clockwise. That's a memorization thing, and that's we kind of need to stick to. The other thing that you need to make sure that you're comfortable with are your distances. So for instance, we were cutting a section 12 foot from the left of A, so this distance is 12 feet. Okay, so if this distance is 12 feet, this, if we look at the problem, this was given as 6 feet. So what is that? It's 6 feet. What about over here? This dimension here was 8 feet. This was 7 feet. And so the entire beam is 30 foot long. That makes this dimension 3 foot. Okay, that might seem silly that you pay attention to get that right. Like, come on, Dr. Mike, we can do distances. Well, I mean, it's something you kind of want to make sure you're comfortable with, because later on, what's going to happen is these distances aren't going to be numbers. Okay, instead of a distance of 6 feet or whatever, it's going to be a distance of X or 30 minus or stuff like that. And I'll go ahead and tell you, when you start introducing the letters, the X's, that I found that sometimes it's like, oh man, hold on, what's the answer here? And then you start doing the problem and the numbers don't quite work out. You're scratching your head, like, what is going on here? And a lot of times it can start from just these distances. So just make sure you take a second and that you're comfortable with getting these. I started out with just doing a problem with numbers because I think that's easy to remember, but we are going to have problems with X's later. And like I said, I only introduce like variables like X when there's a reason to, and believe me, there is a reason to later. Okay, now let's go ahead and share the notebook here. Okay, so now let me take my keyboard off and let's flatten that screen down a bit. There we go. Okay, so this problem, we're cutting a section here. We'll go ahead and draw that out. So this is where we're cutting through the beam. This dimension here is 12 feet. So that's 12 feet. So again, that's where I got that. That was 6 feet, and that was 3 feet. Because later on, like I said, later on, we're going to say, no, that's not 12, that's X, okay? And so that you know, like so, that is coming. So be aware of that. Okay, so what I'm going to do is, first thing I got to do is I got to ask myself, which direction do I look? When I cut a section, do I look to the left or do I look to the right? I want to be crystal clear. It does not matter, ultimately, what direction that you look. You will get the same answer. If you've drawn your components in equal and opposite directions and according to the sign convention that we've already agreed upon, you will get the same numbers either side. It won't matter. But there is something to be said about strategy. There's just less stuff going on to the left than there is going on to the right. So what I'm going to do is cut a section and look to the left. So looking to the left, so what I'm going to do is just redraw what I have here on this left side of the board. So the first thing is just repeat the structure. So AY 5.8 kips. I've got my 20 kip load there. Let's put some distances here. This is 6 feet, 6 feet. And then here's the cut. That's where I samurai sorted through the section. And then you draw your unknown components. So that's positive shear. That's positive moment. If you want, you could go ahead and say, let's go ahead and draw the axial, the positive axial force. But first off, if I sum forces in the x direction, there's nothing going on in the x direction, so it's just going to be 0. So it doesn't really, there's nothing there anyways. But B, even if there is, the axial force doesn't really affect the shear and moment diagrams. So a lot of times when engineers are only focused on the shear and moment diagrams, I've found that a lot of times they just don't write it. And I actually don't have a problem with that, as long as you as the analyst are considering the axial loads in your resulting design if they matter, okay? And later on, when we look at deflections and we look at deflections in trusses versus deflections in beams and frames, there are some other reasons why they kind of get neglected, but I'll talk about that later. Okay, so once you've got your free body drawn, the next thing you do is you just use equilibrium to handle the problem like you would any other. So we sum forces in the y direction, and we say I've got everything going up and everything going down, and you just write it out like you see it on the free body. So I have AY is 35.8 kips going up. I have 20 kips going down, and I have V going down. Now, do I consider the bending moment? Well, we've had these types of problems before. When you're summing forces in the y direction, do you consider concentrated moments? No, because it's not a force, it's a moment. So we ignore that. So 35.8 is V plus 20 kips, and therefore V is 15.8 kips. And that's it, okay? So one thing I want to point out, when you're doing internal shears and moments, there's no direction. Like, I know that I have the arrow drawn downward on the screen or on the free body, and if you want to put down, you can, but really the important thing to recognize is that drew shear according to its positive sign convention. And so since the answer came out positive, really the only thing that we care about is that shear is positive. It's 15.8 kips. As long as you get the fact that it's positive, you're good, okay? Now, let's go ahead and do sum of moments at the cut. Okay, somewhat similar, only there's going to be a little bit more going on because we've got distances. So maybe I can scroll over to the right a bit, give myself a tad more room. All right, So I'm summing them at the cut. And like I said, I'm sort of walking everybody through this because at this point, I think the equilibrium equation should be pretty straightforward with all the stuff we did with reactions and everything we've done until now. I figured this stuff is pretty simple. Okay, so we've got 35.8 at, if I'm summing moments right here, I'm summing them right there. This is the cut. So if I'm summing moments right there, the 35.8 generates a counterclockwise moment. You know, clockwise moment. Sorry, clockwise moment at the cut, and then that moment arm from the cut is 12 feet. Now, the 20 kips, that generates moment in the opposite direction. That's 20 kips in the opposite direction, and that's 6 feet. And then we've got our unknown moment. Do we consider the V, the unknown shear? No, because it's going right through the cut. So the moment arm is 0. So we don't consider that. And so we've accounted for everything. And so we do a little bit of chugging. 35.8 times 12 is 429.6 is M plus 120. And remember, those units are foot kips. And so we get an M, which is positive, and it's 309.6 foot kips. Okay. Like I said, I know today probably feels a bit like movie time, like I'm just sort of doing a lot for you as opposed to being a little bit more interactive, and that's because of the proof that we've got coming up here in a second. But before I move on, are there any questions? I want to take a second and see if there's any questions on this, because I mean, this should be pretty simple. On your homework assignment, I'm giving you 2 problems that are just like this, like what are the internal shears and moments on these 2 beams at particular points. Our homework assignments, actually, both of the problems are in metric, but which ultimately doesn't really matter, but I just thought they were really good problems for this exercise.
Seems just fine. Yeah, I'm not too far removed from statics and dynamics, so this isn't too unfamiliar to.
No, it shouldn't be. I'm hoping it's not. And what we do here in a bit, though, with the graphical approach, you probably did this in statics as well, but what we're going to be doing is shear and moment diagrams for beams, for frames, concentrated moments. We're going to have triangular loads. We're going to have a lot going on, and internal hinges, all the complex stuff we had before that really wasn't complex. We're going to be exploring how that affects our relationships as well. But everybody good? All right. Now, before I go back to the slides, I do want to point something out. So here's the beam, okay, and maybe I'll move this down here. We got a V value of, I think it was 15.8 kips. And the M value was 309.6. Was it 309.6? Yes, foot kips. Now, one of the things I want to impress upon you is that you will get the same answer if you look the other way. Like, for instance, let's take the shear, okay? Let's sum forces in the y direction. Okay, so what do I have? I got 30 kips going down. I've got 18 kips going down. I've got 32.2 kips going up. Okay, so 30 down, 18 down, 32.2 going up. I've got my V drawn upwards according to its positive sign convention. So V plus 32.2 is 48. And so if I subtract, I get V is 15.2. Again, positive number, okay? So if it's 15.8 kips over here, V is 15.8 kips there. Same thing with the moment. Try it out. You will get the same answer, albeit in an opposite direction, equal and opposite, but you will get the same number every time, unless you did something wrong, unless there's an error, in the calculations. So it is a good way to check to see what you're doing. But again, you'll get the same answer each and every time. Okay, let me go back to the slides. Okay, so here's the problem that we did. I do want to ask one question. You know, would our answer change if we changed our point of interest? We cut a section at, say, x equals 12 feet, you know, that being from the left side. What if it wasn't x equals 12 feet? What if it was x equals 20 feet? Or what if it was x equals 5 feet? Would the answer change? Would we still get 15.8 and 309.6 for our shear and moment, respectively? Well, I think if you look at the problem and sort of chew on that a little bit, you find, yeah, the answer would change. We would get different answers where we cut the section. So if you cut a section, you know, at x equals 12 feet, you're going to get a different answer than x equals 13, x equals 14, x equals 15. So if we really wanted to be kind of nuts with this, we could cut a section like at a whole bunch of points, record those values, maybe put them in a big table, and then graph them. And we have a name for that type of graph. We call it shear and moment diagrams. That's what a shear and moment diagram is, and that's ultimately what we're trying to determine. So I just want you to chew on that. Keep that in the back of your head. Now, before we move on to our proof, I do want to mention something. I didn't really think it was valuable to spend too much time in class talking or doing a problem on this, but I thought it was worth at least going through. Now, let's go back to distributed load. So remember, when we compute reactions, we would idealize distributed loads as concentrated effects using the centroid, right? So, for instance, if we have this distributed load here, this is a uniformly distributed load, we would represent that as a point load through the centroid. And same thing if we had a triangular load. Now, when we draw the shear and moment diagrams, and even when we draw internal shears and moments, or when we're trying to determine internal shears and moments, you got to kind of be careful about this. This is a mistake I've seen students make a lot. And so this next slide, I want everybody to really pay close attention to. So let's take a look at this beam. I just made this beam up. So this beam has, it's 20 foot long. It has a 2 kip per foot distributed load from the left support to midspan. And then it's got a 40 kip load right here. I need to fix that. That 5's a little high. I don't know what's going on there. But this 2 kips per foot over a distance of 10 feet, we idealize that as a 20 kip distributed load, a 20 kip point load acting right at this centroidal point. But now let's ask a little bit of a different question. What happens if I wanted to take internal shears and moments like right here? Okay, so let's say I cut a section and I look to the left. I cut a section and I look to the left. That distributed load's different now. It's no longer 2 kips per foot over a distance of 10 feet. It's 2 kips per foot over less than that, like this 6.5 feet. So when I idealize that as a point load, it's no longer 20 kips. It's now something else. It's in this particular instance, it's 13 kips because it's 2 kips per foot over a distance of 6.5 feet. I can't tell you how many times I've seen students have, you know, this 20 kips and they just rewrite it here, and that's wrong. Okay, and so that's definitely something you want to keep in mind. The percent length of the section is the percent of the force. That's exactly right. You know, that's a great way of putting it. It's easy to in the heat of the moment to just in the heat of the moment. I didn't even intend that pun. That just sort of happened. But it's easy to carry on the 20 kip force and just make sure that you don't do that. Okay. All right. Now, this is the money. This is where we're at. Okay. The example that we just did, what it did is it gave us shear moments at a single point in the beam, just at a single place. And that's great for if you want to spot check or if you're just trying to check your numbers. But what if we want the shearing moment everywhere? I mean, like a diagram. That would entail graphing the shearing moment along the beam. And that's our goal, the shearing moment diagrams. We want to be able to plot them, okay? So instead of cutting sections all over the place, you know, the idea is maybe we can be a bit more intuitive and see if we can develop these graphical procedures. There's some rules that we can follow in order to do this. Now, I'm going to go ahead and tell you before we get into this, we're going to be exploring some rules in calculus. Okay. I don't mean that we're going to be taking, you know, the integral of the tangent squared times e to the x. That's not what I mean. What I'm saying is that we are going to be employing some basic rules. You know, like for instance, the derivative of a quadratic function is always a linear function. So for instance, if you look at your shear diagram, if it's a line in one region, then your moment diagram will be a parabola in that same region. And so those types of rules are going to be things that we employ. And the ideas behind, well, what is an integral? An integral is just an expression of the area under a curve in a particular region. That stuff's going to be important. It doesn't mean we're necessarily going to be breaking out, you know, the chain rules or integration by parts. It just means the ideas are going to be pretty important. Okay. Now, in order to try and develop these rules that I'm going to talk about here in a second, I want to talk about this beam. Okay. So first off, the boundary conditions don't really matter. I have it as simply supported. This would really work for anything. I'm just using something to kind of to demonstrate something, and you'll see here in a second why the boundary conditions really don't matter. But I've got this beam, and it's being subjected to some load. Now the load, it doesn't really matter what it is. I'm just going to say it's variable. Okay. But there's a couple points I want to emphasize. Number one, there is a coordinate system. So you can see we kind of have our X and Y axes there on the beam. And the load is, I have the load applied upwards. And the reason I have it applied upwards is look at your coordinate system. The idea is that Y going upwards is positive. So the loads are kind of positive. It just makes the rules that we develop later a bit easier. Okay. Now what I'm going to do is I'm going to take this beam and I'm going to slice out a small element. And when I say a small element, I mean an element that is dx wide. So y'all remember from calculus, again, this isn't like breaking out the quotient rule or anything. It's just talking about the ideas in calculus. So remember, what is dx? You know, remember start defining limits and derivatives. You know, you've got this change in x, and as that change, that delta x approaches 0, you start approaching that infinitesimal element that we call dx. That's just an element in the beam that's super tiny, like really tiny. Okay, so we'll slice out an element that's dx wide, and then we're going to zoom into that element. Okay, and so what do we see? Well, there's a couple things that are worth pointing out. So first thing is to look at the load. Okay, so we've got this like variable load that could be, you know, all over the place, but keep in mind, we're now looking at an element that's super tiny. I mean like thin, okay? So on this super tiny element, we can assume that the load is constant, okay? It does, I mean, because it's so tiny, the load really isn't going to change very much. But what we are interested in doing is not really the change in load, but we're trying to figure out what's the change in shear, what's the change in moment, okay? Because the idea is from one point to another, if we understand how much the shear changes and how much the moment changes, then we can determine an expression to plot. And so that's why there's a dV and a dm term. The idea is like on one side of the element, we have a shear, and then the other side, we have a shear plus some small change, or on one end we have a moment, and on the other end we have a moment plus some change. The idea is that the shear and moment will change from one side to the other. And so now that we've got this element, and that element is just a free body diagram. And so if you have a free body diagram, you can use the equations of equilibrium to solve for those unknown components. Okay, so we have that the shear, so let's sum forces in the y direction. So everything going up is positive, everything going down is negative, although, you know, just everything going up equals everything going down. So I've got, if I look at my free body diagram, what do I have? I've got V going up, I've got E plus dV going down, and then what do I have here? Well, it's not W going up. Remember, this is a distributed load. So it's how do you idealize a distributed load as a force? It's the load times the length. So width, or the distributed load W times the width, dx. So instead of W going up, it's W dx. So V plus that distributed load going upwards equals this component going downwards. I can solve for dV as equals this. All right, what about summing moments? Well, summing moments, I need to sum moments about one side of the element. Doesn't, or actually, no, I really don't. I can sum them from anywhere, but I just figured it was easier to sum moments from the right side. So summing moments from the right side, what do I get? Well, the V plus dV, that goes away. And what do I have? I've got moment, going clockwise. I've got this shear here on the left, so V times dx, contributing moment. I've got this. Now, what's the deal with this? Okay, so this one might be a little weird. So how did I come up with this part right there? Well, that's the force, okay? And this part is the moment arm, right? And how do I get the moment arm? Well, that's my idealized force, and I'm summing moments from the right. How far is it from the right side to the resultant? It's dx over 2. Okay. And then on this side, I just have m plus dm. Now, when you chug out all your algebra, you get this, big old long equation here. Well, what's going on here? So you have w dx over 2. Remember what dx is. Dx is an infinitesimal element. It's a super, super tiny number. Well, break out your calculator. What happens when you take a really tiny number and you square it? You get a really tiny number. And so a lot of times in our derivations, what we'll do is when we have these higher order terms, and that's what I mean by a higher order term, there's a differential element square, we just neglect them. So we cancel this component out, we can cancel that out, and then we have an m on either side that we can cancel. And so there you go. We get dm is v dx. Okay. So I'll go ahead and tell you that is the pain is over. We can relax. No more crazy calculus for today. That's basically it. But what we have is a relationship between loads, shears, and moments. The idea is that if I have my load diagram and I integrate it, I get my shear diagram. And if I have my shear diagram and I integrate it, I get my moment diagram. Okay. Now, for the most part, we're not going to actually be straight up computing derivatives. Like we're not going to be computing integrals. Like I said, no integral of tangent of the x times e to the x squared, nothing like that. Instead, what we're going to be doing is recognizing some patterns. So for instance, if you have, let's say, your shear diagram, one of our graphical approaches is, well, if I have the shear diagram, and if I compute the area under the shear diagram, the area under the shear diagram will tell me how to plot my moment diagram. And a lot of times our shear diagrams look like what we had here on this previous slide. Like if you look at this shear diagram here, that shear diagram is just a bunch of rectangles and triangles. And so to give you kind of an idea of how this works, I mean, what do we have here? Let's take this shear diagram, okay? So this shear value is 46, okay? Now, this distance here is 10 feet. So what is the area under this box? Well, it's 460, right? Please forgive me, I'm drawing this with my mouse, so it's horrible. So that area is 460. And so that's how we get that number right there, because the value on the moment diagram is equal to the area under the shear diagram, because the integral of shear is moment, okay? What about the shape, right? Well, this is a constant, right? That's a constant, right? Remember when you graph a line, you get a constant. Well, go back to calculus. What is the integral of a constant? Like what happens when you integrate a constant? What do you get? You get the constant times x, right? You get the integral of a constant is cx. Well, what does the graph of cx look like? It's a line, right? So that's why, we go for, that's why this value is 460, and that's also why this is a line. And so we just use those rules to construct this shear diagram, and I promise you it's as simple as that. It's that simple, okay? Let me fast forward a little bit. So what I think is most important for you as the analyst to be able to plot these shear diagrams is not, okay, going back and opening up your Math 229 notebook and trying to remember how to apply the chain rule or implicit differentiation or, trig substitution for integrals in Calc 2. That's not what I'm talking about. Instead, what I think is most important is that you understand some basic rules for plotting and some basic relationships for derivatives and integrals. And so this is something I kind of want you all to chew on for the weekend, because we're going to start to use this stuff on let's say, on Monday. So first thing I want you to understand, and I want you all to maybe make sure that you're comfortable with this, is some of the basics of plotting. For instance, let's pop quiz everybody. Let's take this line right here. Does that line have a positive slope or a negative slope?
Positive.
Positive, right? There you go, exactly right. Okay, that's the type of stuff that is important, okay? That's the type of stuff that's important, okay? Understanding that that's a positive slope. Understanding that this line has a high slope, this line has a low slope. What is the slope of that line right there? There you go, 0. Exactly right. So again, I'm not going to make you do derivatives and stuff, but I do want you to kind of understand this stuff. I also want you to understand the derivative and integral relationships that you get, specifically with polynomials. I will go ahead and tell you that if there are any derivatives and integrals that we do in this class, it's going to be limited to polynomials. So, well, I mean, like, what's the derivative of x squared? 2x, like that stuff, okay? So what I mean by that is stuff like this. So, for instance, if you have, let's say, a uniformly distributed load, so your load looks like this, okay? So a constant load. If your load looks like that, I'll go ahead and tell you that in that region, this is what your shear diagram is going to look like. And if your load looks like this, then your moment diagram, or I'm sorry, if your shear looks like that, then your moment is going to look like this, okay? Excuse me. That understanding that trend of how you go from like load diagrams to shear diagrams to moment, to go from constant to linear to quadratic, that's pretty. The idea that, okay, like right here, that's a high value. So at that same point, we get a high slope. Here, we have a low value. So low value, low slope. See, on Monday, I'll start calling that things like lot to a little. So our shear diagram will have a lot of shear to a little shear. So our moment diagram, a lot of slope to a little slope. That type of stuff, if you're comfortable with that, shear and moment diagrams are not only going to be fun, they're going to be simple, okay? And that's basically it. I don't really have anything else I want to talk about today. Monday, what we're going to do is we're going to start taking these relationships and we're just going to start going to town with them. We're going to start simple. We're going to treat it like a lot like what we did with reactions. We're going to start simple. We're going to start with concentrated loads, and then get into distributed loads, and then get into concentrated moments, get into what happens when you have an internal hinge, how does that affect things, and all that stuff. At the very end, we're going to do a couple of things that are going to be a little bit symbolic. We are going to look at deriving equations for shear and moment. Again, not because I'm turning into a math guy, but because they are important for later. And we are going to see if we can try and use Excel to plot some of these, because I think it not only is useful, but it does help increase your understanding of it. That's all I have, everybody. Your homework's due Monday. Y'all have a wonderful weekend. Oh, wait, is there somebody have a question?
Can you go back to slide 10 for a moment? I think you have a typo there. Underneath.
Oh, you do. Right here?
Yeah, where it says that. Yeah, that's
Yeah.
it.
You are right. That is supposed to be V. I'm going to fix that, and then I'm also going to fix the, there was another typo with that 5 being raised. Thank you for that. Thank you. Yeah, I'd have missed that. Just full stop, I'd have missed it.
All
But
right.
yeah, that is supposed to be V.
All right. All right. That's all.
Thank you. I'll get that fixed. All right. Anything else? All right. Well, I'm going to stop the recording. You all have a wonderful weekend. Stay safe. Stay healthy. We'll see you on Monday.